All right, let's jump right in. Today, we're going to talk about one of the most powerful ideas in all of software, object-oriented programming, or OOP for short. Now, we're not just going to cover what it is. More importantly, we're going to get into the why, the huge problem it was created to solve. Okay, so let's set the scene here. At the very heart of OOP is this one single challenge that every single developer runs into eventually: software complexity. As our programs get bigger and more powerful, they just have this natural tendency to get, well, messy, really messy. Sound familiar? I bet it does. You start off with this really clean, simple idea, but then you add a feature and another one. And pretty soon your code is this giant tangled web. A tiny change over here somehow breaks something completely unrelated over there. This beast, this tangle, is exactly what OOP was designed to tame. So how in the world do we fight back against this complexity? Well, OOP gives us a completely different way to look at the problem. It's a huge shift in perspective. Instead of thinking about a program as just a long, long list of instructions, we start thinking about it in terms of these neat, self-contained things called objects. This right here, this quote, gets to the absolute core of the whole idea. See, older ways of programming focused on the actions, the verbs, what the program does. But OOP just flips that completely on its head. It says, hey, let's focus on the data first, the nouns, the things themselves. The actions then just become something that those things can do. It's a much, much more organized way of building software. Now, to really get objects, you first have to understand what a class is. Think of a class as a blueprint. It's the plan, it's the cookie cutter. It defines all the properties and all the things something can do, but it's not the thing itself. An object, on the other hand, is the actual cookie. It's a real, concrete instance that you created from that blueprint. So you can have one blueprint, one cookie cutter, but stamp out dozens and dozens of individual cookies. And this is where the magic really happens. It's so intuitive. We're not dealing with a bunch of disconnected functions anymore. Instead, we have, say, an account object. It holds its own data, like the account balance, and it also has its own behaviors. We call these methods, like deposit or withdraw. It's this perfect little self-contained unit that actually mirrors how we think about things in the real world. Okay, so this whole object-centric way of thinking is held up by four fundamental principles. People often call them the four pillars of OOP. Let's take a look at how these pillars all work together to help us manage all that complexity. First up, we've got abstraction, and this is all about making things simpler. Think about it. When you drive a car, you just use the steering wheel, the gas pedal, and the brakes. You don't need to be a mechanic and understand exactly how the engine works. Abstraction is that same exact idea in code. It gives you a simple way to interact with an object while hiding all the complicated stuff on the inside. Next is encapsulation. This is like putting all the important parts of the engine inside a protective case. An object's data is bundled up tightly with the only methods that are allowed to change it. This is so important because it stops other parts of your program from just reaching in and messing with data they shouldn't be touching. It's a huge deal for security and for preventing bugs. Then there's inheritance. This is an awesome tool for reusing code. Why write the same stuff over and over, right? So if you have a general vehicle class, you can then create more specific classes like car or bus that just inherit all the common stuff from vehicle. Then you can add their own unique features. It perfectly models this is a relationship. A bus is a type of vehicle. And the last pillar is polymorphism, which is a fancy Greek word that just means many forms. And what this lets us do is use one single name for lots of different actions. So building on that last example, we could tell any kind of vehicle to move. And if that vehicle happens to be a car object, it'll drive. If it's a boat object, it'll sail. You just call move, and the program is smart enough to do the right thing. It's incredibly flexible. Okay, a quick but really crucial point here. Inheritance, that is a relationship, is super powerful, but there's another way to connect objects. Composition, which is a has-a relationship. A car isn't an engine, right? But a car has an engine. And knowing when to use one versus the other is a massive part of good object-oriented design. In fact, a lot of pros will tell you to favor composition over inheritance because it often makes your code more flexible and way less fragile down the road. So we have all these powerful principles, but how do they actually help us build software? Well, it's not chaos. It follows a really structured process, moving from a high-level idea all the way down to the actual code.
The whole thing starts with analysis. That's where you just figure out what the system is supposed to do. Then comes design. This is the how. This is where you create the blueprints for all your classes and figure out how they're all going to talk to each other. And only after you've got that solid foundation do you move on to implementation, which is, writing the code.
And that design phase is so critical. Good developers don't just open a text editor and start typing. They plan. They often use visual tools to create diagrams that act like an architectural blueprint for the software. It shows all the different pieces, what kind of data they hold, and what they can do. It maps out the entire system before the first virtual brick is laid. And then, finally, that blueprint gets turned into real, working code. So here's a simple student class. See that little word private next to name? That's not just for decoration. That is encapsulation in action. It means nothing outside of this student object can directly mess with the student's name. They have to go through the official public set name method. This is how that blueprint becomes secure, reliable code. So we've walked through the problem, the mindset, the principles, the process. So what? Why go through all this trouble? What's the ultimate payoff that has made this idea dominate software for decades? Well, here it is. This is the why. Every single one of these benefits, managing that crazy complexity, reusing code, being flexible, making things easier to fix later on, every one of them is a direct result of the pillars we just talked about. By thinking in objects, we build software that's organized, that's adaptable, and that's just way less likely to break. We finally get to tame that beast of complexity. And that brings us to one last thought to leave you with. The real world isn't static, right? It changes all the time. A truly well-designed, object-oriented system is built for that change. Its flexibility means it can evolve right alongside the real-world problems it's trying to solve. And that, ultimately, is the real power of thinking in objects.